Okay, so welcome everybody to our October FPGA seminar. Apologies for technical issues as our streaming website had major changes and we're still, hopefully you can see us and things will continue. So today we actually only have one talk, so you have more time than you thought you had. So today this is a rehearsal for a reconfig talk in December. So it's Kaveh Asari and Andreas Moschowitz.
Thanks everyone for coming in and everyone for joining online. So the talk is about SPREX, a soft processor that we worked on which does Runahead execution. So this is our upcoming talk in reconfig basically. So why do we choose Runahead? Well, what we're targeting here is applications that have irregular instruction level parallelism. That means it's not easy to observe them before the application is actually gets to run. So you need to extract this parallelism at runtime while the application is running. That makes it a lot harder to extract it and identify it and exploit it. What are the alternatives besides Runahead to exploit irregular parallelism in the application? So we can do superscalar. That's one really old-fashioned way of exploiting parallelism. And we got out of order. And besides that, we got Runahead. So, well, we know in the past we've demonstrated that the superscalar has its own disadvantages on FPGAs, mainly because of the forwarding path. You need very huge multiplexers, a lot of interconnect usage. That does not really go well on FPGAs. Out of order has its own disadvantages too. A lot of new components on top of the in-order pipeline we need, and very new, like the components that we need are not designed for the FPGA fabric. So it's not really beneficial to do out of order. Yet, we don't know. Someone has to actually sit down and look at it. There's an out of order core developed in the Santa Cruz University of Santa Cruz, USC I believe, which uses about 180,000 LUTs to do an out of order core, to have like a running out of order core. That's quite a lot of LUTs to have one soft processor that's like 20% faster than an in-order pipeline, or maybe like 50% faster. But that's still a lot of overhead in terms of area. So we chose Runahead. Well, the basic. So when we look at Runahead, it's based on a simple in-order pipeline. So it's really simple, and you add just a few functionalities on top of this in-order pipeline to get this functionality of Runahead execution out of it. And let's take a look at how Runahead actually works. So in normal execution, we execute instructions. The moment we hit a cache miss, we stall the processor, we wait for the memory to come back. When it comes back, we continue executions, normal execution of instructions, and then we keep doing this. We go through this cycle. We hit a cache miss, we stall, we wait, execute, again, hit the miss, and stall. Now, the idea behind Runahead is, what if we could overlap these two memory requests? What if I could just find them in advance and send them all together, pipeline them, send them to the memory controller so I don't have to wait for them sequentially, and then so I can gain some performance here. So in Runahead mode, in Runahead execution, we will be running in normal mode until we hit the first cache miss. Then we will switch to Runahead execution. Now in this mode, whatever we do is going to be discarded anyway. It's at the end. So the result doesn't matter. All we're looking for is to find the second miss. We already have the first miss. We want to find the second miss as soon as possible so we can overlap the request, the retrieval of those data from the memory. So we initiate the second miss as soon as we figure it out. We continue execution until the initial miss comes back. The initial data that we asked for from the memory comes back, and we switch back to normal execution. And by the time we reach to the point that we needed that data, hopefully that data is already in the cache, and we don't encounter that second miss anymore, and we basically gain that much performance improvement. But Runahead, we have to have some functionality to do this thing. And a simple in-order pipeline cannot really do this. So let's see what we need to do Runahead execution. The very first thing we notice here is that we have multiple memory requests pending at the same time. That means our cache must be able to send these requests to the memory controller simultaneously. Like, it should be able to process subsequent requests while it's actually waiting for the first data to come back from the memory controller. So that means we need a non-blocking cache. We actually need non-blocking cache for another reason too. Just sending out a memory request is not the only reason that we need a non-blocking cache. Imagine we want to, so the goal is to find subsequent misses. Now, in order to get there, we need access to the memory hierarchy. So if the cache is waiting for the first miss, like the first miss is initiated, if the cache is waiting for that, if it's not able to respond to any subsequent accesses to the cache, then we have a problem. Because a lot of operations that we perform on the processor need access to the memory hierarchy, like the cache. So not only it has to be able to send multiple requests to the memory controller at the same time, it must be able to respond to those requests that actually hit in the cache too. So our non-blocking cache must be able to do both. Now another requirement. When we go into the run-ahead mode, we make modifications to the state of the processor. But because this is a speculative execution, we don't want anything to be visible outside of the run-ahead execution. So anything happening in that dark blue area has to be discarded. Now, there are ways of accomplishing this. One of the easiest ones is to create a checkpoint when we go into run-ahead mode, and then restore when we come out of it. So we need a checkpointing mechanism here. We need to be able to, for example, our register file. We need to be able to checkpoint it. When we're done with run-ahead mode, we need to restore it. So when we're done with run-ahead mode, right in this point, it's as if nothing had happened in run-ahead mode. It's just all we wanted to be visible was the state of the cache to be changed, so that the second line that's going to be requested in the future is in the cache. So we need checkpointing there too. What else do we need for run-ahead? When we go, imagine the first miss that we encountered to initiate run-ahead execution was a load, right? Now, all the instructions inside the run-ahead window that need the data from that load, they're not getting that data, right? So, because the load is not here, the data is not here, right? And what if, there's a tree of instructions, data paths, so we need to be able to track these invalidity of data and say, any instruction that's using these values are not producing valid data. So we need to be able to somehow track valid data in our processor, basically our register file, and say any instruction that falls into that tree of data, and we're not going to execute it because it's not really producing valid data. So we need register tracking too. Now let's see, I'll talk about more requirements along the way, but let's see how we actually do these things. So for the non-blocking cache, conventionally what we have is a cache, like a storage, tags, like a regular blocking cache, and then on top of that we have a misstatus handling register. What it does is, it says, what are the lines that I've already asked for from the memory controller, so that subsequent accesses come in, I know I don't have to ask for them again, so I don't send multiple requests, and at the same time I know I can have the cache visible to the processor. So the processor can access the cache, but it's accessing MSHR at the same time to know what lines are pending, what requests are pending. Now the problem with MSHR is it has cams. It has lookup, like really huge cams, like 32 bits wide, because it needs to look up addresses. At most you can reduce it down to 30, and And it's not really efficient on FPGAs. Like the moment you have these huge comparators, it goes slow, it goes big. We don't really like it. Now, for non-blocking cache, we use NCore. NCore is a non-blocking cache that we proposed recently. And the way it works, and the way it actually replaces MSHR is that it actually gets rid of it altogether. What we do is we say, for every line in the cache, what I want to know is that line pending or not. So all I have to do is have a single bit there that says, is this line pending or not? If it is, I cannot access this line. So this line is locked. So any access that comes, any subsequent access to this specific line is blocked. Basically, we throw that access away. There's a drawback to this. There's a reason MSHR was proposed initially, because what if two accesses from two different addresses map to the same line? These are not logically the same. These are not the same addresses, but you cannot address them in this scheme. But what we realize is that these don't happen that frequently, and the performance penalty that we get is about 2%, less than 2% actually. So what we concluded was that it's not really worth it to have such a huge structure, like a huge CAM, just to gain 2% in IPC. And that is, notice that that's IPC, it's not overall performance. So frequency-wise, NCore is a lot faster, so overall the performance would be a lot higher. All right, now for checkpoint. The main thing that we need to create a checkpoint of is the register file. We have this huge, we have this 1024 bits of data. We need to create a checkpoint of when we switch to Runahead mode, and then we need to restore it when we're done with Runahead. Now, copying is bad. If I were to copy the whole register file into another separate bank and work on that, and then copy it back, work on my original copy, and then when I want to restore, copy it back, that takes multiple cycles. And we have about 10 to 20 cycles in Runahead window to begin with. So we don't have time to make a copy of the register file one by one register at a time. And we need to do that. If we want to copy, we need to go one row at a time because we're using block grams. And we don't have that many ports to access the block gram. So what we do is we use CFC. CFC is a checkpointing mechanism we proposed a while back that is actually voice copying. And because of that, we can freely use block grams. Now, how do we actually use this to checkpoint a register file? So what we really need is one checkpoint, because there's not going to be multiple levels of Runahead execution. We only have one level of Runahead execution. We're either in normal mode or in Runahead mode. So we only have two modes. So we replicate the register file in two, and all we have to do is say, which ones am I going to use? The original register file is using normal mode, and the second register file is used only for data that's produced in Runahead mode. If I'm using any data that's been produced before in normal mode, I get it from the original register file. Any data that's produced in Runahead mode is stored in the Runahead register file. And all I have to know is which one is producing the latest result. And that's where CFC comes in. It tells me exactly which register file to use and gives me the latest data. The more details about CFC are in that paper, I suppose. And how does it actually get implemented when we put it on FPGAs? Well, we have two logical register files, but they actually map onto the same block RAM because they're small enough to fit into one block RAM, and all we have to know is the address that that actual register resides in, right? So they both fit into one block RAM, so we don't have any overhead in terms of block RAMs. It's just we have very small selection logic before the block RAM, specifying which part of the block RAM to use. So that ends up being really fast and really efficient for checkpointing the register file. Any questions so far? Yep.
Right, so could you also just write to both? I guess you have to replicate block RAMs to do that, but if you have two physical block RAMs for each register files, you could write to both all the time and just read from the second one in Runahead mode. So you don't.
If I write to both all the time, then I'm ruining the one that's supposed to act as my checkpoint.
Sorry, and then when you're in Runahead, you only write to the.
Exactly, that's exactly what's happening. So Runahead register file is receiving all the updates happened in Runahead, right? And any data that any read goes to prioritizes Runahead register file over the original register file. So if I have any data produced in Runahead mode for that specific register file, I get that. Otherwise, I'll go back to my checkpoint.
Okay, we can talk about this later.
Okay. All right. Now for register tracking, it's a simple tracking of valid data, valid bits. For every register, we put a 1 bit saying, is that an invalid data or not? So if initially we have a load that missed, we mark that register that was being produced by the load as an invalid register, and then any subsequent instruction that uses that data and also produces data has its destination register marked as invalid. And we clear that bit if an instruction actually produces a valid data. So if, let's say, come along is an instruction that's using immediate values, or some other register that has valid data and overwrites that register, we just clear that bit. It's, the overhead is like we need 32 registers for the 32 architectural registers that we have. All right. Now this. Oh yes.
Yeah. How do you track that through conditional branches? So
Why
if
does that make it different?
if you have a piece of invalid data,
Mhm.
and then there's something that tests that data in a conditional way.
Oh, okay, good. We don't. So, okay, maybe I should talk about this. So, in Runahead mode, it doesn't really matter what we do, right? At the end of the day, I'm discarding all the results.
Right.
So, as long as I'm somewhat accurate, that's okay. I don't have to be precise about the execution, right?
Okay.
So I can, branch prediction is a guess to begin with, right? I mean, you correct it along the way, but the whole thing can be a guess. So because I'm guessing the next cache line that's going to be used anyways. So as long as I'm somewhat accurate, I'll show later that we are, then it works out, right?
Okay.
But you're right, we cannot be precise, we cannot be certain that that's exactly the outcome of the branch. So on top of all this, we have in Runahead mode, we have certain things we have to avoid. If well, if an instruction is using an invalid data, we discard it. So we need extra decoder for that inside the decode state. And if an instruction is accessing IOs, that's a permanent change to the state of the whole system. It should not happen because in Runahead mode, logically nothing is happening in Runahead mode. From outside world, from outside the processor view, the only thing that's happening is more requests to the memory hierarchy are coming in. Nothing else should be visible. Yes.
If you're in a memory map system, how do you then distinguish between accesses that go to I/O and accesses that go to memory and the cache?
We have like a specific region for like datas and specific memory for region for IOs. And on top of that, we have a specific instructions for IOs in NEOS 2 ISA. So that actually could be a problem if someone doesn't follow that, guidelines, I guess, because in NEOS 2 ISA, you can have the last bit as a 1, indicating that it's actually an I/O. So it could be a little bit problematic, but yeah, we avoid those. And if an instruction is causing exceptions, like if it's a trap instruction, or if it's like, what else do we have? Like e-return instructions, or any of those that change the processor state. And those that change some other parts of the processor state, like if it changes control registers, right? If I'm disabling interrupts, I shouldn't really do that. That's not something that should be happening inside the Runahead mode, in Runahead mode. So we need an extra decoder inside the decoder stage to identify the instructions that have to be discarded. All right. So overall, well, the gray ones, the gray stages are regular, typical textbook style 5-stage pipeline. And on top of that, what we have is extra decoder. Extra decoder for Runahead. We have register file modified CFC. We have register tracker, and we have the non-blocking cache and core. So these are all the additions to the 5-stage pipeline. Now let's see. So the processor that we actually synthesized is a 5-stage pipeline. Is using a bimodal branch predictor. It's actually fairly accurate, and the instruction cache is blocking, so we don't really. There was no need for having a non-blocking cache for my cache, and the data cache is Core 32 kilobytes, and cache line 32 bytes, and so Core is actually capable of sending out 32 requests at the same time. So it can't track 32 requests, outstanding 32 requests. We never really go that high because we don't have that much time in Runahead mode, and mainly because memory latency is not that high in this environment. And well, our caches are direct mapped. We use CFC for checkpointing, and we only have one checkpoint because that's all we need. Now, our environment is, we do very large implementation. We use Stratix 340. We don't really need that big of a chip, but just to have used it. A little, like this year's Chorus, but a few points version load. And we clock the processor at 133 megahertz. We have 1 gigabytes of DDR memory on the board, running at 266. And so on top of our processor, like we synthesize the processor and then load an image of UC Linux, and then on top of that load the benchmark, and then run those, and then benchmark them, like get the cycle. The way we collect data is we skip 1 billion instructions from the beginning of the benchmark, and then collect data for the next 1 billion instructions. So that first 1 billion is to avoid all initialization, so we get to the actual behavior of the benchmark. You can actually visibly see that the benchmark is doing something, instead of like printing out stuff. Yep. So let's first get into some stats about the processor. Like when we synthesize it, we get about 1700, we use about 1700 ALUTs, about 1500 registers. These are not like different registers, they're packed together. And we use 7 block ramps on top of caches. 7 is for, 2 is for register file, 1 is for branch predictor, and 4 are in the Encore. And that's for tracking outstanding requests. And the extra decoder turns out to be really small. We don't really need to do much. And register tracking, as expected, 32 registers for tracking, and the decoder there, and all the logic to update it ends up being 83 ALUTs. Encore, so this number 149 means the overhead of using Encore. So if we were to use a blocking cache, we would have used about 250 ALUTs. Now, because we're using Encore, we're using 150 more ALUTs. And so in total, we're imposing about 20% more ALUT overhead, and about 20% registers. And considering caches, the block ramps for cache, we impose 5% only block RAM overhead. But if we don't consider caches, that looks high, about 57%, but that's not really a fair comparison, because the cache is in the processor too. If you wanted to replicate the entire processor, you would need those caches too. And without the cache, the whole Runahead doesn't really work out. So So yeah, overhead-wise, area-wise, it's not that is actually really good. So I'll see how it actually performs.
Oh.
Yep.
So the ALET column, does that include the registers?
Yes.
Everything, and then
And then
specifically
of those, exactly, yeah.
Okay.
Of those we have 1500, yes. So, should be blue, but anyway. So, these are the, oh, I didn't talk through this. We're using a SPEC 2006 integer benchmark, and only part of those, not all of them. Because some of them didn't compile with the GCC for user Linux. Some of them are using really, it just didn't compile. And it was kind of impossible to compile. That's what I had to change the benchmark. I didn't want to touch the benchmarks otherwise. I mean, it wouldn't have been the same benchmark. And but this ends up being a good subset of the integer suit. And so what we see here is, on average, we get about 10% speed up, which is fairly okay given the area overhead that we have. And well, for example, for some like A star, this is an XML parser, VZ2, it's about more than 10%, which is nice. You would say, you could argue that it's not as expected, like you would want to see more speed up, but I'll talk about that. Right. So about 40% for A star and 10% on average.
Sorry, question
Yes.
related to that. What are you comparing against? What's your base case?
Oh, the processor itself with Runahead turned off.
Okay, so it's exactly the same. Everything else is the same, right?
Mhm.
It acts like a regular NEOS or whatever it was.
Yeah, yeah.
Okay.
What was the question? Say that again.
Yeah. You answered my
Okay.
question.
What's the baseline?
Yeah.
Yeah.
What kind of average are you computing with?
Kind of average,
Yeah, is it
geometric mean.
just geometric mean?
Yeah. And yes.
So if I did not have any Runahead hardware, would the processor run faster, or I mean, would it clock faster? Because if you're using the same.
That's a good point. Yeah, I'll talk about it. Yeah. Okay. Now we want to see what effect does running in Runahead mode has on the memory bandwidth usage. Because you're putting more pressure on the bus, power usage is higher, and all that. So we see on average we're putting about 12%, like 10% increase on the bus. For some, we see a lot of increase, about 100%. And these are, if you actually look at it, H.264 doesn't really get that much of a performance boost. That is because we're fetching we're polluting the cache. It's fetching those lines that it actually never needs. It's evicting lines that it actually needs later. So all the performance boost that it potentially gets is actually offset by the performance loss of evicting useful lines. So that actually leaves some room for future work. And on top of that, a good phenomenon happens with Runahead, and that is branch prediction accuracy. So what happens is, the moment you go into Runahead mode, you're actually looking ahead into instructions that you would be executing in the future. And by doing that, you're actually training your branch predictor. So by the time you go back to Runahead to normal mode and want to execute those, you've already trained your branch predictor. It's already encountered those branches, and it's better trained. I wouldn't say it's fully trained, but it's trained more. So what happens is you get lower misprediction rate, about 13% decrease in misprediction rate, which is quite significant. And so this actually ends up, so some of the boosts in performance could actually be because of the better prediction accuracy. All right, now that was basically it. So what I want to emphasize here is that Runahead is not, well, there are a lot of counter arguments for Runahead. You know, that the performance gain is not really worth the area overhead. Well, there's like about 20% area overhead, in terms of lots. But one thing we should note here is Runahead is benefiting a single-threaded application, and that's really key point. That's the key point here, because recently the research has steered towards like making, like boosting multi-threaded performance, multi-threaded applications performance. And I haven't seen that much of it work on single-threaded application, like work on single-threaded applications. And it's, well, sometimes it happens you have an application that's, you know, like these, that's running in single-thread mode, and you need to have more performance. It's not easy to get that performance. It's not easy to extract that parallelism out of the benchmark. And it's, I would say it's a good start to use Runahead on soft processors. So what we need to do to make Runahead better? Like I would say, Runahead can easily pollute the cache. The small predictors could be used inside the cache to avoid fetching, like fetching lines that are actually polluting the cache. We can have predictors by cache lines, like metadata by cache lines, saying that these lines are really important to this benchmark. Do not evict them in Runahead mode. And yeah, so yes.
Yeah, it might be easier just to turn off Runahead if you detect cache
If you,
pollution,
exactly, yeah.
because obviously you're executing something.
Exactly. You could be, you could use Runahead just to train your branch predictor. Do not initiate or evict any cache lines. Just train the branch predictor, or because 30% change in branch prediction accuracy is actually good. So you might end up benefiting from that. Depends on the processor architecture. Depends on the number of stages you have. Depends on the prediction accuracy you start with. Yes.
So yeah, for some of the benchmarks you mentioned that basically most of the benefit come from training the branch predictor, right? So you could turn
No,
off,
I wouldn't say that. No, I wouldn't say that.
but could you, for example, make an experiment and just turn off actually feeding anything into the cache,
Yeah.
and just train the branch predictor and see what's the soul to isolate the benefit of cache versus the benefit of training the branch predictor.
Yeah.
You see, like, or the other way around. Just feed the cache, but don't train the branch predictor. Like, don't update any of the.
Don't have any. Yeah,
So
exactly.
To,
Yeah.
to basically like
Yeah.
decouple those
Yeah.
factors.
That would be like, I believe that they can work on that in like basic work, like for processors, like, you know, actual.
But that, I mean, but this wouldn't be.
Yeah, but in this
complicated
environment,
in your
yeah,
case, right?
exactly, yeah.
It's
That,
like
that
a-
could be something,
Okay.
exactly, yeah, that's good.
So I also have a follow-up
Yeah.
question. So regarding the Fmax, so what's the maximum frequency in the baseline of the baseline? Without adding any of the Runahead
It's
stuff?
about 180, something around there.
So what's the critical path?
Oh, where does it fall through? Like,
Critical, why is like, what is the slowest part of the process? I assume
multiple things, like because we're using a 5-stage pipeline, it's forwarding from the memory, from the cache.
Because NEOS reports for a 5-stage pipeline up to 300, depends what you put into it.
For
Yes.
5-stage or 6-stage? I think it's 6-stage. NEOS F is
fast,
6
I'm not sure
stages.
if fast is 5 or 6, but
Fast is 6, yeah. And that actually makes a difference. Like when you have 2 stages for memory, that's the way NEOS is. It has 2 stages for memory.
But
And
so if you were to have that 2-stage, you would also get that max?
working on it.
Okay.
Yeah, so I was going to say, so the next stage would be to improve the clock frequency. We're working on that. We'll study the critical paths and see. So just to give an overview, the major paths that fall are problematic are forwarding, branch predictor, if you want to do fast branch prediction, like same cycle branch prediction, and like major ones would be, yeah, all kinds of forwarding. Like,
This is
'cause you
almost
have-
like a NEOS 2, right? This is almost like a mirror copy in terms of microarchitecture, right?
yeah,
So basically.
NEOS 2S, like the one that we have right now, not NEOS
Okay,
2F.
so yeah, so basically, you should be able to like.
I don't know what frequency NEOS 2S gets. Do you
I
know?
think they're all on Stratix 3. They're all around 300
Yeah.
almost, and then
I never
the course
tried
on Stratix 4 for unknown reason.
The only thing that Well, Neos 2S doesn't have data caches.
News to us.
Yeah, it only has instruction cache. So that actually makes a
But
difference.
it's just that-
I'll
Okay,
look
we
it
can-
up,
we can
yes.
go over it later.
Yeah, it doesn't have, yeah.
Yes, a few follow-up questions for Devor involving frequency and baselines and so forth. So,
Mhm.
not clear, your baseline, you're using your same processor also?
Exactly, yeah.
But, and when you say you turn off the Runahead, do you mean you remove the hardware, or do you just disable it, like, don't use that path while executing?
It doesn't, it never moves, it just blocks the processor whenever you have.
Okay, but the hardware is still there, and
Yeah.
therefore still affects your critical path and operating frequency. So,
Well, they both run at the same frequency
Oh,
to make
okay.
it, I guess, more.
but shouldn't you
Yeah.
be comparing it against a processor which does not have that hardware and all the Runahead critical paths at all? Like, wouldn't you get a higher Fmax if you completely removed the
True.
Runahead hardware?
I guess we wanted to compare. I don't know. In my view, that was I don't know. It's
Okay, because like you said, if a Neos runs at 180, you said 180 megahertz. That's more than 10% faster.
oh,
than,
Neos technically runs a lot faster.
yeah. So shouldn't you be comparing your processor to Neos? Would you get a slowdown then? Like.
So
it's
what
the same
what
architecture.
we're really demonstrating here is not. Is basically demonstrating the potential you would get from Runahead execution,
Okay.
not just this specific implementation, right? So we're saying that if you have a processor running at X, and if you put Runahead on top of that, you can maintain that frequency.
And you maintain that frequency. That's the.
Then this is
assumption.
the speed off you would technically get.
So basically the benefits of IPC.
But it's
Assuming-
of IPC, exactly.
Assuming you
Yeah,
manage
exactly.
to keep the frequency up or within a small margin, you would get this benefit from IPC, right? So,
And the other thing I want to point out is at higher frequencies, the potential for Runahead is actually higher. Because the higher your frequency, the clock frequency of your processor is, the higher the latency of the memory is. And then you have more time, more number of cycles to actually execute in Runahead mode and fetch new data. Yes?
Yeah, under the caveat that at higher frequencies, when you add Runahead, it would not slow down the.
Exactly. If you can maintain frequency, exactly. Yeah. So what I would say is that if you can, so yeah, if you can increase.
Were you able to maintain frequency for the baselines? So when you had your regular 5-stage pipeline
Mhm.
and you added Runahead, did it keep the frequency keep the same or did it drop?
I think I saw about 10% drop. If I remove everything and if I was like, you know, if you actually hand tune it a little, I'm not saying place and routing hand tuning, like, you know, your code is actually written well. I saw about 10% drop. Yes.
Is there an instruction prefetch on this?
Instruction prefetch, you mean like,
Anticipating the instructions to come and trying to prefetch them.
no, there's no prefetcher. Like, you mean, yeah, no, no.
Because it just struck me that that if you have a jump instruction, for instance, that you're going to have a instruction cache miss,
Mhm.
and you can't use Runahead because you don't have the instructions yet.
Well, exactly.
But if you had some sort of prefetcher, then this same mechanism would allow you to, in fact, continue running, find the misses in the potential code, you know, in the code that was there.
So basically, instruction cache would be non-blocking too. So because you need to be able to prevent. What the reason we didn't really go along that path was instruction cache hit rate was high to begin with. It's
Mhm.
about 97%. So we didn't really see much potential there.
Okay.
Yeah.
So, I know you mentioned that the critical path right now is through zero memory, right?
Yes.
So, seeing as though when you're in Runahead mode, you don't really care what's coming back from memory because you're going to discard all the results anyways. Is there a way to create a shorter path there and then run at a higher frequency possibly during Runahead?
True. Yeah.
Because the path is through your cache.
I've
and back,
seen-
right?
Like when so what you're saying is there's a mux that data comes from the bus or from the data cache.
Right.
Don't go after
Just
the mux. Just use the data.
Use
comes from.
like,
Exactly.
You can use
So
garbage
even if you
data.
do these, I actually went over all these data paths. That's makes big difficult. So yeah, I went over all these, and you get like incremental, you know, gain in frequency. So you get about like, you go from 150 to like 170 when you do that. And then the multiple paths in parallel are holding us back, so it has to be worked on as well. But major things are forwarding, and not just the data path, the control path too, like to decide where to forward from. And yep.
So, so basically, so we talked about most of the benefit you get from like feeding some useful data into the cache that you need later, right?
Yes.
Okay. So, could you measure how much would you have to increase the cache size to get the same benefit? So, Runahead versus processor without the Runahead but with a larger data cache, and at which point you get the same 9% IPC. You see what I'm
Yeah.
getting? Like that would be
When
really
I-
interesting because some people will be, or some, you know, if I have a lot, if I can just put more block RAM at it,
Mm-hmm.
or use the block RAMs that you use for Runahead.
Mm-hmm.
If you use those same block RAMs for the,
So when you go
bigger
from
cache.
4 kilobytes to 32, you get about 5% IPC for these rangements and this in this environment.
but what cache did you use? What was the size in the previous?
This is 32.
Okay, so if you went to 64, let's say,
I don't think I could fit that.
64 kilobytes
I don't think I could fit
on
that.
SPREX 3,
Yeah, I don't,
I'm pretty sure it's that.
because there's like 32 kilobytes of iCache too, right? So,
Yeah, there's megabytes of stuff on
Pretty
Stratix,
sure
on the
it's
Stratix 3 chip.
It's also spread across the chip.
Well, doesn't matter, like. Yeah,
Are you
so,
sure it's-
so,
I think it's megabits. It's not megabytes. I think it's about
I think you have
a
a,
few megabits of data on the Stratix 3. I think I tried 64. I could be wrong, but I can't say for sure.
that'd be interesting because you could show that increasing the
Mhm.
cache might be really practical. So the only way to actually have better IPC would be with this, right? I'm not saying that the cache might perform better, right? Or the Fmax might drop severely when you increase really the cache, right? Depends how it's laid down.
That's the point. Fmax does actually drop. Like when you go from 4 kilobytes to 32, the encore itself frequency drops from 305 to 270. So, like the cache alone cannot perform more than 280.
Because
270 to 80.
yeah, because block RAMs are getting bigger and bigger with each generation, right? They were like 4K, 9K, now they're 20K.
Mhm.
Maybe Stratix 6, 40K, you know. So sooner or later, 2 blocks RAM, huge cache, right? So
Yeah. And 40K you're talking about, that's 4 kilobits.
yeah, Stratix 5 is
That's
10K, so I'm assuming
kilobytes.
40, they're going to 40K in Stratix 6, right? Which is, yes, but that's a trend. If you
No, I agree. Yeah, that's true.
So
And one thing I want to, it's kind of irrelevant, but the smaller the cache, the better the higher the performance gain for Runahead, because you have more potential there. And the other thing I want to point out is having a bigger cache. So the performance gain you get from increasing the cache is kind of orthogonal to performance gain you get from Runahead. So these are like different things you can gain.
no,
right?
absolutely.
That's like, so basically with a bigger cache, you're looking at history, you're saving history. With Runahead, you're bringing in future, right? So these are two different things. Considering you don't have loops, right? Assuming you don't have loops. Basically, cache saves your history, Runahead brings in future. So these are two different things. So what I'm saying is, if you increase your cache, you can still gain from Runahead. Yes?
So right now, when you have one register file, that's your, like, your checkpoint.
Oh, okay,
you
good.
run ahead a register
Mhm.
file. On the first miss, run ahead register file is going to get the stale data.
Yes?
Right. And let's just say you come back from the cache miss, you continue regular execution, and you have another cache miss. The register file from Runahead might still have a lot of stale data in it. Does it cause problems?
So what we do is, let me go back.
He only reads from the register file.
Exactly.
Oh.
So this guy, CFC, has a small table that resets the validity of these data whenever you switch to Runahead mode. So the moment you start Runahead mode, any Runahead mode, it doesn't have to be first, second, right? The moment you start Runahead mode, you set all the bits in the second register file as invalid. If I need any data from register file, because that's invalid in the second register file, I go for the second one, for the original one, right? At any time that I produce any data in Runahead mode, I write it into the Runahead register file, and then set that bit to valid. Next, if I need it, I prioritize this over my original register file. So I'm getting the latest data. But I've never changed my original register file. That's why I needed mux there, and right. So that's basically prioritized mux. Yes.
So if you're throwing it away every time you start Runahead, wouldn't that mean that if you had overlapping cache misses, that you would be starting from even more stale than otherwise register values? Because you would be resetting your third cache miss back to whatever the original was rather than whatever you had done in between? Is that intentional? Or?
I don't understand why I would be resetting the cache.
You were saying that every time Runahead starts, that you reset all of the, you flash all the bits. So
Yeah.
that would mean that if you had one cache miss outstanding, and while you're still running ahead for that, you hit another cache miss, you'd reset all the registers that have been set?
Oh no, if you're in Runahead mode, and you encounter a miss, that doesn't cause another Runahead mode initiation. So,
Okay.
yeah. So only the first miss that you see. So basically, only misses that you see in normal mode count.
Okay.
Yep. Oh, yeah, I think. Oh.
So understand why A star was that much better than the other ones in your...
So basically, it happens that you fetch useful data instead of. So the tree of instructions, the ones that actually end up using data, you can find them. They're not that far along the path. They're closer to the ones that you actually first see missed. And
Just got lucky.
yeah, exactly. So pollution is less.
Just a quick one.
Yep.
You're going to be using these slides, I assume. There's a typo in the second line of
It's checkpointing.
the checkpoint.
I think I've added that to the dictionary. That's why. Oops, that's why, yeah. Because, I've examined.
How do you ensure that your Runahead register file has the most updated values after you come out of Runahead mode? Because you could actually have incorrect values.
So when we
in
end
Runahead.
Runahead mode, we don't really care about that register file anymore.
Right, but on the next entry of that register file, because I'm assuming you're going to be updating your Runahead register file even in normal mode, right?
So look at it this way. The second register file is only a filter. You're only going to this first, to your register file. You're reading data from that guy, right? If you write, you don't go through that filter. In Runahead mode, if you write, you only write, you stop at your filter.
Okay.
And if you read again, you're reading that daily data that you wrote into your filter.
So when you clear your bits at the end, then you never use the filter.
Exactly. Yes.
As for the software side, could there be any compiler optimizations that would generate code that's more beneficial for a Runahead processor?
Yes, you can have independent instructions closer together. Like if you have a chain of instructions that are using the same, down the same, data flow, interleave these instructions. So they're not that far along, they're not that far from each other. You can find different memory loads or stores that, access different cache lines faster. But it actually takes, you have 20 cycles for the data to come back. If it takes you 15 cycles to reach to the point that you see the second miss, you're only saving 5 cycles, right? But if you had seen it 10 cycles in advance. Yep.
So it seems like this would work best if you had something like reconversion branches, right? Where the miss that you have, it looks dependent because the processor pipeline can only see 3 instructions in the future. But if you go 10 instructions down, it turns out that branch doesn't even matter, that you're comparing against the memory miss that you're waiting on, and you can kind of run ahead that way. So maybe that would be why A started so well, if it had a reconvergent branch pattern. But it seems like if you're pointer chasing, this is going to be useless. Right, and if it really, like, if you were.
Exactly.
If
If
you were drilling down.
the
that
second, yeah, if the second, the subsequent users are dependent on the actual load, yeah, exactly.
Yeah, so it
So
seems
it's-
like it's places where there's dependencies that maybe a really large out of order window might have been able to find, maybe not, like reconverted branches, for example.
Some of the like some of the benefit actually comes from the local data too, like the storage that you use for local data. So yeah, it's not all about fetching the data that the benchmark is storing, like the programmer wrote. It's local data that you're using, like local variables are stored in the stack. You're basically prefetching your stack. A lot of yes.
This copy-free checkpointing is pretty clever. Is it one of the main contributions of the paper, or is this a known technique?
It's a previous paper we had in FPL. It that was basically proposed for checkpointing the renamer, register renamer. So in out of order, you need to rename registers from architectural to physical, but the mapping you have to checkpoint it whenever you see a branch, because you speculatively update that map, and if you miss a branch, you have to restore it. Now in there, you actually need multiple checkpoints. Like we show that we need like at least 4 to get a good performance. So what you do is you have 4 of these, and you prioritize over them. Like you have a last checkpoint and a second last, you go through them. And that search actually ends up being done with only 1 lot. Because you got like 4 inputs, 2 signals saying which one is your last, then you have to wrap around it, find the first one. So a 6 input lot does it. And actually ends up being fast, yeah.
The memory bandwidth overhead that you had, what are you measuring there? You're measuring the total number of memory fetches over the
Yes,
the
we're
benchmark?
not looking at burst to see how bursty the memory gets.
Okay, so that's entirely overhead. You're not being, some of it is not due to the fact that you are running faster, right? That you are doing more work in a unit of time.
No, it's not. So it doesn't account time exactly. Yeah, less than 5.